So it's my great pleasure to introduce Dr. Danilenko, who's now at Toruń. He's my author, as you can see from the title. He will talk about the irreducible Koopman representations for groups of automorphisms of rotated trees.
Thank you. It's my pleasure to talk in this institute. This is again the scheme, but it's about construction of irreducible Koopman representations of some groups of automorphisms of some special graphs. So the purpose is to construct explicitly a family of irreducible unitary representations for a family of countable groups. The groups are of combinatorial nature, by which I mean uncountable and even more, in some sense, unclassified. In fact, there are many concepts of unclassifiable, but here we mean some family is indexed as family of representations which are indexed by elements of some bad topological space. Okay, later on. Combinatorial origin means groups of symmetries of some infinite graphs. So we'll consider only spherically homogeneous rooted 3T. There is a graph, probably one of the most simplest infinite graphs. So we have one root, and we have a sequence 1, 2, and so on. It's a graded graph. On the first grade, level, on 0 level, we have one root. On the first level, we have Q1 root. On the next step, we have Q1, Q2 vertices. Every vertex from the previous level is joined with from the first level is joined with Q2 vertices from the next level, and so on. And so on. So this is called an infinite rooted tree. And we are looking for bijections of this graph, which preserves the structure of the graph. So all of such bijections are called automorphisms, a group of automorphisms of G, T. And we'll be interested in countable subgroups G here. Example is Grigorchuk, a famous Grigorchuk group. In case of Grigorchuk group, all 1 to 2 and so on equal to 2. And the group is generated by several generators. It's finitely generated. A, B, C, D. We consider 4 generators. So let me first explain how generator A acts. So this is my tree. the left-hand side, the right-hand side. These triangles means everything that is full. So A is just a flip. Just a flip. Next B, generator B. So consider the left-hand side of the graph. And consider a flip here. So until now we define our B on the half of the graph. Okay, and here it's not defined yet. So it will be defined on the next steps. So on the next step, I look subgraph that starts from this point. And this again looks exactly like the entire graph. So I again divide it into two parts, and on the left hand side I consider a flip. Okay, so now my B is defined, how to say, on 340 of the graph, and it's not defined on the subgraph starting from here. So I again consider that next step, and here it's just an identity. On the left hand side, it's just an identity. And then I start to repeat. So on the first,
all the time is B, or you?
it's all the time B. Yes. So B somehow corresponds to sequence of steps. Flip, flip, identity. Flip, flip, identity. And then I start to repeat. Flip, flip, identity. That's also infinitely. So this will be B. This will be my B, generator B. Generators C and D looks in a similar way, but C corresponds to flip, identity, flip, and D corresponds to identity, flip, flip. Which means I start to construct, for instance, D. Again, consider my graph divided into two parts, left and right. And first of all, identity. Okay, then I took the right hand side. Take flip here. Okay, then applies to this vertex. Flip. Okay, and then start return to identity, and so on. Identity and so on. Like that. So I have defined A, B, C, D for generators. Altogether, they generate subgroup G, first Grigorchuk group. The group is very interesting because it has a number of nice properties. These properties are easy to get. Bright properties. The order of every element for Grigorchuk group is a power of 2. The power of 2. And this is important property. Next one, each non-trivial normal subgroup is a finite index. Next property, G is residually finite. The growth of G is intermediate faster than polynomial. From here it follows that G is not important, not very important, but slower than exponential. So for instance, it does not contain a subgroup with free subgroup with two elements. This was an answer to Mueller question. Another property of G, that G is amenable, which means that it contains a sequence of Turner subsets, but it's not elementary amenable. That is, it cannot be obtained from finite groups and abelian groups using operations passing to subgroup, passing to quotient group, and countable intercalary.
Is it possible to give a heuristic why the intermediate blocks? Or it's not
It's rather involved.
So it's not clear. I mean, because I wonder how he came up with this idea that this will be not clear. Okay. We don't know whether I have it's fundamental.
From observing that if a group has a polynomial group, then it is virtually important because we do not have even only. No, it's polynomial. It's no.
Okay, so if it is not polynomial, then it is.
No chances to be. But on the other case, it does not contain subgroup to generate pre-group.
And the last property is concluded from the one from the last property, right?
Yes. So let T be a spherical homogeneous rooted tree. Then the group of automorphisms of T has a structure of infinite rest product. What is an infinite rest product? Well, first of all, the definition of a rest product, classical, the most the simplest when two groups are finite, A and H are finite, and H acts on a finite set omega. Then the regular rest product is a semi-direct product of A power omega across A. Where the action of H on A omega is given by this proposal. Now, suppose we have an infinite sequence of finite groups AM, and everyone acts on a certain finite space omega n for each n. Then A2, A1, this group, acts naturally on this group. Indeed, how to define this action? So, because this group is a semi-direct product of this group and this group, it's enough to define how this group acts and this group acts. A1 naturally acts along the second coordinate. And this group acts on say, fiber-wisely along the first coordinate. So for every omega, we have fiber omega 2, and omega 2, we have and we can continue and notice that this group is well defined and it acts on the product of three spaces omega 1, omega 2, omega 3, and so on. So finally, we can define the infinite regularized product as just as the projected mean. So every arrow is a natural projection from semi-direct product to the corresponding proportion. So now, if T is spherically homogeneous root of 3, then we can consider finite set Xn consisting of Qn points, and then group of bijections acts naturally on the corresponding set, bijection on Xn, X on this set. And then we can produce infinite rest product. Infinite rest product, like that. Bijections. The group of bijections of X1, and then rest product is bijection on X2, bijection on X3. So this product is going to find that it's easy to show that it's exactly the group of automorphisms of T. Now, definition of boundary of the tree. This is the set of all infinite simple ways on T, which start at the root. Simple means without loops. Of course, this space can be identified with the infinite product x1, x2, and so on. But then it is a compact counter space. Is the natural topology. Here we define cylinders in the natural way. And of course, every cylinder is Koopman, and every Koopman subset is a finite union of cylinders. And the group of T induces an action on the boundary by homeomorphism. If our T is endowed with the natural product topology, then of course it's compact and totally disconnected, and it acts on the boundary in a continuous way. Moreover, this action is transitive. So compact group acts on a compact space, everything totally disconnected. If G is a bijection on the boundary, then we can specify which bijection belongs to the group of automorphisms of tree. This happens even only if G has a special structure, it's a triangular structure. We can project the G to how to say, to first coordinate, to first two coordinate, to first three coordinate. For every n, we can project D to the first n coordinate. This property completely determines the G element of the automorphism group. Now definition of the product. And if we denote by PM the projection from X to X1n, then G composition PNG will give us the composition GNPN, where GN is some bijection of the first of the set product of the first n coordinates. And we can even write a coordinate formula for every transformation from group power. So every element G which belongs to our T has the following structure, where gamma is a bijection of the first coordinate, and alpha 1 and alpha 2 are maps from x1n, the product x1, x2, and so on until xn, to bijection of the next x and x1. So this gives a formula for all automorphisms of the tree. which we will use later. Okay. Now let G be a countable subgroup of T, and denote by Gn the image of G under Gn. Then Gn acts on x1n, which is the product x1, x2, and so on. This action is minimal if and only if Gn is transitive for each n. If G is minimal, then there is a unique invariant probability measure lambda on X. Of course, lambda is the product of the equidistributions on Xn. So it does not matter which G we choose. If we know that G is minimal, then there is the only one invariant G invariant measure on X. Let's call it Koopman, product of equidistributions on X. Grigor-2 group is minimal. Moreover, it's possible to check that the orbit under Grigor-2 group of every point is just the tail equivalence in the class of X. But there are, of course, minimal groups G, such that Gx is a proper subset of the tail equivalence relation class of each X for each X. For instance, that's a very simple example like that. Consider this space, which is, of course, can be used as a boundary of a 3P. Dialectic 3T. And let G be direct sum. Of course, G acts on dt. So it's a subgroup, it's a group component. G is a countable subgroup there, so there is a natural action of G on this space. And this action is free, of course. And G orbit of every X is just the tail equivalence class of X. Tail equivalence class. 2 points are called tail equivalent. Tail equivalent. If there is n, such that it's n equals to yn for every n greater than a. And if you consider H subgroup of G in G such that some sum of all coordinates is 0, G belongs to G, which means that G is a sequence of elements G1, G2, and so on, and starting from some point, we have zeros. So we can say about sum of all coordinates. Because in fact, we have on the finite domain non-zero coordinates. So if sum is 0, then H is of course a subgroup in G. And it's easy to see that H is minimal. X in the minimal is minimal. As a transformation group. So H is minimal, but the H orbit of every X is not equal the tail class of X. Just Rx is the union of two disjoint class, Hx union H some X star. But H is minimal. Okay, and there is another interpretation of a minimal.
Just to note, you can even make a number of components uncountable.
Yes, possible. There is another interpretation of minimal G actions on X, where G is a subgroup in out T. Don't want to go into details, but suppose that we have a sequence gamma n, decreasing sequence of subgroup in G. And they decrease, and their intersection is either trivial or consider even homogeneous to H. The intersection can be non-trivial, but if we consider another sequence, gamma 1, gamma 2, is trivial, where this is the largest normal subgroup inside gamma n. Once more, gamma 1, gamma 2. Decreasing sequence of subgroup of finite index. Finite index in G. And gamma n, the second G, gamma G minus 1. So this is already normal subgroup. Gamma n. The largest normal subgroup in gamma n. Then, of course, we also will have the decreasing sequence already normal subgroup to finite index. So we assume that this is trivial. So we consider those subgroups that the this intersection is trivial. And then we can produce a sequence of homogeneous space, finite homogeneous space, gamma quotient 1, gamma 2, gamma quotient 3, because arrows compute equivariant, G equivariant, and pass to projective unit. Then we'll obtain a G action on some projective space X. No, it's called anodon. It's called anodon. So all actions which appear as action of minimal G on out T, all of them are odometers in this sense. Another important concept that we need is a concept of branch group. So for each G, element of G, denoted by support G, the set X where G is not trivial. Then, of course, it's an open subset in X. And given an open subset O, we denote by GO those elements in G whose support is entirely in O. So we see some interaction between space and time. O is the subset. O is the subset in X in the space. GO is the subset in G. The time, it's time. So the group GO is called the rigid stabilizer of O. If O1 and O2 are disjoint open subset of X, then of course, these groups GO1, GO2 compute. Then we can consider product, just algebraic product of groups where this open set is just a cylinder of length n. Consider all possible cylinders of length n. For every cylinder, we have an open subgroup. We have a subgroup G indexed by this cylinder, and the product is normal in G. The product is normal in G. Definition. Let G as usual be a minimal subgroup of T. G is called range if for every n this normal subgroup is of finite index in G. Is a finite index in G. And G is called weak range if this group is not trivial for every y, for every cylinder. And let me just a simple observation that weak every branch group is weakly branch because these two groups are conjugated. So if the product for finitely many conjugated group is not, when it's not trivial, then every one group from this product is not trivial. Okay, ask.
G, Y, and 1.
Here is a notation. Whenever we have an open this is a subgroup in G. This is a subgroup.
Yes, and this Y and
this is a cylinder. Cylinder of length from yeah. Consider all. Yes, this is a field.
Individual cylinder.
Yes. So Grigorchuk group is branch. And there are
branch.
yes. Look here. This is a normal subgroup in G. But product, just algebraic product of groups. Groups elements they groups pairwise elements from this group or from different. So the product is again group because commutativity. And then if it's a finite index for every n, n is a rank of a cylinder. Okay, and then G is called branch. Okay. There are a lot of other important branch groups in mathematics. For instance, they appear iterated monodromy groups in some problems related to classification of infinite groups and so on. I just refer to survey branch groups by Bartoldi, Grigorchuk. So my purpose is to construct Koopman representation. For that, I need non-singular actions. So currently, I have a group, I have space. This is infinite product space boundary of the tree. And now I want to define measure, such measure that with respect to this measure, G acts non-singularly. So I will consider to descend the simplest possible class of measures. Namely,
the previous slide, which is perfect.
I will consider infinite product measures. So I consider all non-atomic infinite product measures on the boundary of the tree. So now take an element G belonging to which is an automorphism of the tree. Then you know that it has the following structure, where gamma is a bijection of x1 capital and a1 and 2 and so on, and maps from product of the first coordinate to bijections of the next coordinate. There was explanations. Just a general form of any automorphism. Now definition. Suppose that
there is nothing yet about the variance.
no, not yet.
You want to mixtures.
Yes, but I want first of all I want non-singularity. This is not real. So first of all, so the following definition: if there is n such that G does not change any coordinate starting from n capital, then G is called finitary. Okay, so this definition does not depend on any measure, pure algebraic. But if it depends on measure, so for every x, for almost every x, there is some n such that starting from this n, no one coordinate changes starting from n capital. Then the G is called mu finitary. Next concept: if for every epsilon there are n and a global subset A such that mu A is less than epsilon, and G changes no more than n first coordinates for each x out of A, then G is called purely infinite. Let us compare second and third. Of course, if G is mu finitary, we also can find for every epsilon some n capital and some subset A, Borel subset A, even closed, such that measure is less than epsilon, and G changes no more than n third coordinate of each x out of A. But this set is not necessarily closed. It's closed, should be closed, but not open. And we have an example which shows that yes, it's possible. There is G which is mu finitary but not pure. Denoted by A nu and A nu valid the sets of all finitary, mu finitary, and purely mu finitary constellations. They are groups, and if G belongs to one of them, then measure is non-singular. That's why they were introduced, just to get non-singularity. A group G is called finitary, mu finitary, or pure mu finitary if G is a subset A nu, or A nu valid spectrum. Because I have an example which shows that whenever we have two orthogonal measures on S, then it's possible to construct minimal G such that the first measure is such that the G is finitary with respect to the first measure, but not finitary with respect to the other one. And in example 2, in the situation when x1, x2, and so on are simply possible, just 0, 1, then for every lambda, it's possible to construct so-called Bernoulli measure. So the infinite product of m lambda with itself. infinitely many times, where m lambda is just a measure which gives measure lambda to 1 and 0 minus lambda to 0. Now fix any theta from an interval 0, 1. Then it's possible to construct a minimal group G here, which is mu theta finitary, but not mu lambda finitary for any lambda different from theta. And it follows, it's possible to check that G will be non-singular with respect to mu theta, but not non-singular with respect to mu lambda. Lambda is from theta. Okay. In case of Grigor-Chuk group, we have 4 generators, A, B, C, D. And it's possible to write down these formulas for coordinate formulas for every of the generators. This is definition. So this is second definition, which is equivalent to this one. This one is combinatorial. This is algebraic. Okay. And it's easy to see that whenever we have an infinite product measure mu and x, G is mu finitary. Moreover, it's purely mu finitary, but not finitary. Hence, G is mu non-singular for every infinite product measure. Okay, whenever we have non-singular actions, we can produce a Koopman representation, which is a unitary representation of the Verkin group. Here is the definition. If G is a countable group of transformations on X, and every transformation preserves the class of mu, then we can construct a Koopman unitary representation of G in L2 Y mu by the well-known formula. This is I remind what ergodicity is. An action G is called ergodic if there are no invariant subsets, except for subsets with zero measure and full. We would like to produce irreducible representation, but of course that is without invariant subspace. But if G is not ergodic, then the corresponding Koopman representation is never irreducible, because if we can consider a subspace of functions supported at an invariant subset, and this is an invariant subspace. So we need first of all construct ergodic. So how to produce ergodic? We know how to construct finitary measures, which implies that the action will be non-singular, but that's not enough. We would like to have ergodic. For that, we will use so first of all definition. Suppose we have probability measure of X. G is a group of non-singular transformations of X. And we say that G is compatible with mu if for every n there is a small larger than n, greater than n capital, and subset A y prime inside cylinder y from 1 to n, and elements of groups elements G y prime from G, such that these properties are satisfied. If G is compatible with mu, then G is ergodic. So what is the meaning of this concept? How to check that G is ergodic? What does it mean? This means that whenever we have two disjoint subset, then it's possible to move first subset to the second in such a way that they overlap. Overlap on a measure of positive measure of the overlap is positive. And move with an element of a group. But of course, we have too many subsets. It's difficult to check this everything. So instead of taking any two possible sets, let's take only sets which generate the entire sigma algebra. For instance, in our situation, cylinders. So we want to check ergodicity on cylinders and somehow deduce ergodicity on the whole space using ergodicity on cylinders. But for that, we need more than just ergodicity on cylinders. And what does it mean? What does it mean more? We want to move on a significant proportion. Take any cylinder here. And we want to move a significant proportion of this cylinder to another cylinder. And even this is not enough. We want that the Radon-Nikodym derivative is constant on this significant part of the cylinder. So our transformations, our elements G, Y, prime, they are in a sense piecewise affine. So on the spaces partitioned into finitely many pieces, and on every piece, G, transformation G multiplies matter on some constant. When we pass to another atom of this partition, then this constant may be different. But and this holds not on the whole atom, but on a significant part of the atom, which is more than 90%.
Just a comment. If G is minimal, then we can move any cylinder of nth level onto any other cylinder of nth level. But the tricky condition is the third one, to make sure that on large proportion of the cylinder, G has the same Radon-Nikodym derivative. So that the key condition here is mentioned.
Yes, and this is very important because if you drop this third condition, then we cannot deduce the limit. The problem with passing to the limit. Problem will be when the try to approximate an arbitrary step. Then but then you pass to another. You say that this large will be, how to say, very small. Small will be large.
So the question so here is it important that G acts on 3 because somehow the construction can be made just on contour sets, considering not necessarily actions preserved in the P structure.
Yes, possible to abstract our general situation, but we consider only this. But surely some structure is needed. Good structure of cylinders. Now we want to construct lots of measures which are compatible with minimal perpendicular. So lambda n denotes a distribution of lambda n. The infinite product of all lambda n is called harmonic of X. It is invariant under any group G. G is inside the group of automorphisms. And suppose that G is minimal, and G is a purely finitary of this lambda. So G preserved lambda. And this is our assumption on G. And then for each n, fix two measures two measures Bn0 and Bn1 on two probabilities on Xn. Then it's possible to find an infinite subset N such that for every omega infinite sequence of 0, 1, G is compatible with the infinite product measure lambda omega, where lambda omega is like that. And moreover, G is purely finitary for every such measure lambda omega. So let me draw a picture. This is M. So our purpose is to construct N1, somewhere N2, N3, so on. And for every sequence of 0, 1, we define a measure lambda omega, which is like that. If a point is different from N1 and 2 and 3 and so on, we just put here the corresponding lambda. Lambda 1, 2, and so on. But in this coordinate, in coordinate N1, we put beta n, and here we take omega n. Here we put beta n, beta 1, omega 1. Here is beta 2, omega 2. Here is omega beta 3, omega 3. And so on. So all the other measures between these vectors are lambda, the corresponding lambda. So we took the Haar measure and then modified it in some positions. So N1 and 2 and 3 and so on. So it is possible to choose this N1 and 2 and 3 in such a clever way that we'll have this problem. G will be compatible with every such measure. You see, this second coordinate is chosen in a random way. So for every choice of omega, we have different measure, lambda omega. So for construction, we use induction, of course, induction argument, and the previous one. Now let me remind what is Hellinger distance and what is Koopman theorem. Koopman theorem about orthogonality of infinite product measures. Suppose that we have two measures, mu and nu, which are infinite product measures from the very same infinite product space x1, x2, and so on. So Koopman answered the question when these two measures are orthogonal and when not. So he proves that dichotomies. The infinite product measures can be either equivalent or orthogonal, and nothing in between. The first case happens even only if this infinite product is positive, and they are orthogonal if this infinite product is zero. Definition of Hellinger distance. And then from Koopman theorem and our theorem, we can deduce that if P n0 and P n1 are sufficiently large, far from each other, more than delta doesn't depend. And moreover, they are each of them, this measure is far from lambda n is far, then if we use this construction, then we obtain measures with the following properties. This lambda omega, every lambda omega will be non-singular and ergodic with respect to G, and they are equivalent if and only if omega and omega prime are Taylor equivalent. If omega and omega prime are not Taylor equivalent, then the corresponding measures, lambda omega and lambda omega prime, will be orthogonal. And moreover, every lambda omega is orthogonal to the Haar method. Now, let me set the
Question. So we have measures lambda omega depending on some continuity of the parameter omega.
Yes.
It's possible to formulate exactly in which sense we have continuity.
Now, irreducibility of Koopman representations. Suppose we have an ergodic group of non-singular transformations on a probability space and denote by a K nu the corresponding Koopman representation of H. Denote by every bounded function f on Y the linear operator f linear operator by multiplication by f. And suppose that for every such f, the operator LF belongs to the von Neumann algebra generated by all Koopman operators. Then kappa nu is irreducible. It's very easy. How to deduce irreducibility? So suppose let A be an operator which commutes with every kappa nu. But then due to this property, the operator LF belongs to the von Neumann algebra generated by all of them. It follows that A commutes also with LF for every F. But you know that L infinity is the maximal abelian von Neumann algebra. Maximal. Hence, every operator that commutes with every LF also of the form LF. Now, this property commuting with kappa nu G gives immediately that F is invariant under G for every G. But G is ergodic, hence F is constant. So only a constant operator commutes with Koopman representation, which means that this Koopman representation is irreducible. Okay. Next, But irreducibility is not, ergodicity of the action is not enough to obtain irreducible representation. Because if you have just a single transformation, that action, ergodic or non-ergodic, doesn't matter, the corresponding Koopman representation is never irreducible. Is never irreducible. So we need something more to prove irreducibility, something more than ergodicity. And this something more will be the property of branches. For a subgroup G, I remind that GO is the set of G which are supported in O, and IO the set of fixed vector for all this group. The lemma: if mu is an anatomic probability on X, and the let mu be orthogonal to the harmonic. Suppose that G be branch and mu non-singular. That's where you branch. Then for every cylinder 4, we have a nice description of this invariant subspace in IO. So this is the subspace of vectors which are fixed under every transformation from GO. So it looks very nice. We can explicitly describe this space as the set of all functions supported out of O, in the complement of O. So in particular, the projection, orthogonal projection to this space is just the operator of multiplication by indicator of the complement to O. And now theorem on irreducible Koopman representations for branch groups. Let mu be non-atomic measure on X, and let G be branch, mu non-singular, and ergodic. If mu is orthogonal to lambda, then kappa mu, the Koopman representation, is irreducible. So this is where this branch is important here for irreducibility. Idea of the proof. Denoted by n mu, the phenomenal algebra generated by kappa mu. Fix a cylinder O in X. Then the orthogonal projection P to the subspace of fixed vectors for the full group in GO belongs to this phenomenal algebra. But then it follows from the amount that P is L1OC, which means that this projector belongs to phenomenal algebra. But then the complement, this complement also belongs to this algebra. In turn, this implies that multiplication by the indicator of any open set belongs to this phenomenal algebra. Hence, the same is true for NF, where F is arbitrary bounded function. And so we see that for every bounded function, NF belongs to the phenomenal algebra generated by the Koopman representation. So we can apply theorem of irreducibility. Now we always assume that measures which are interested in are orthogonal to the Haar measurement. And why we avoid Haar measurement lambda? Because G preserves lambda. And G is a subgroup in the group of all automorphisms. which is compact. And the whole this group also preserves Haar methodology. So we can extend Koopman representation of G to the Koopman representation of this group. But this group is compact. And hence, by Tether-Wade theorem, every representation can be decomposed into orthogonal sum of finite dimensions. So we have a contradiction. Impossible. I mean, it's impossible to get irreducible representation if we consider the Haar measurement. Now, about equivalence, so we have very many Koopman representations, and we know that all of them are irreducible. Next question to find out when they are unitarily equivalent and when they are orthogonal. We can answer this question in the following way. If G is branch, non-singular and ergodic, with respect to both mu and mu prime, then if mu is equivalent to mu prime, then of course kappa mu and kappa mu prime are unitarily equivalent. If the measures are orthogonal, then the representations are disjoint. Idea of the proof. The first is obvious, and for the second, if mu and mu prime are orthogonal, but the corresponding Koopman representation are unitarily equivalent, there is a unitary isomorphism B between these two spaces, x mu and x mu prime, with this property. And from here we can deduce that instead of this operator, we can put projection, orthogonal projection to IO, and here projection to IO in this space for this cylinder, and then from here we can deduce that the same somehow is true for here we put L infinite, LF, where F runs over bounded functions, and then we somehow apply a theorem about isomorphism, star isomorphism between two L infinite spaces. We know that every such isomorphism has a spatial origin, so it's generated by point-wise isomorphism, which takes measure to an equivalent one. And because of this property, this isomorphism is trivial. So trivial isomorphism take one measure. Equivalent measure means that these two measures are equivalent. And now we can formulate the main result. Denoted by P of X is the set of probability measures on X. And though this space with the weak topology. Then it's a compact Polish affine space. Denoted by P infinity, the subset of infinite product probabilities. Then it's a closed subset in P. Now main theorem. Let G be a branch, a subgroup of A lambda bar. This means that G is a purely finitary with respect to the Haar measure. Then there is a continuous from 0, 1, n with the natural topology to this space, which is followed, such that G is non-singular and ergodic with respect to mu for each sequence omega. Moreover, the corresponding Koopman representation is irreducible. Moreover, if two sequences are tail equivalent, then the corresponding unitary representations are unitarily equivalent. If the sequences are not tail equivalent, then the corresponding Koopman representations are disjoint, not unitarily. Okay, so you see we have parameterized non-unitary equivalent classes of representations by tail equivalent classes of sequences here. But while this space is good Polish space, but when we pass to quotient by tail equivalence relation, we obtain a very bad Borel space. It's not standard. So we constructed a lot of inequivalent unitary representations, but they are parameterized by the Borel space. So a large constructed a large. Next, let me remind a concept of weak equivalence of unitary representation. Suppose we have two unitary representations of the same group. They are representations in Hilbert spaces H and D, respectively. Then the first one is weakly contained in U, U is weakly contained in V, if for each finite subset F in G, for each vector H in H, and for each epsilon, there exist finitely many vectors T1, Tk, and T, such that this inequality holds. For every G is F. G is a finite, F is a finite subset in V. This concept is important. For instance, it's possible to use it in definition of a amenable group. G is amenable even only if the trivial representation of G is deeply contained in the regular group. And if U is deeply contained in V and V is deeply contained in U, then V and U are called weakly equivalent. Weak equivalence is an equivalence relation. And of course, if two representations are unitarily equivalent, then they of course are weakly equivalent, but not vice versa. So let me just formulate a theorem that in addition to our main system, we can state that all representations that we constructed, K mu, which we know can be either equivalent or disjoint, nevertheless, they are weakly equivalent. So they are not so far from each other. So they can be not unitary equivalent, but they are. Okay. Probably the last slide. Let me say that this work was motivated by two previous works by Artem and Grigorchuk, where they considered similar problems, but slightly different. But they under other restrictions. They considered T very special, such that Q1, Q2, and so on, all of them are equal. And they considered only Bernoulli measures. 1 equals to 2, and so on and so on. But on the other hand, they considered more general groups. They considered weakly branch groups, while in the present work we consider only branch groups. And it was claimed that if G in those papers, if G is sub-exponentially bounded, there is a definition of this concept. This concept is more or less in the spirit of pure finitarity. And under this condition, it was claimed that the corresponding Koopman representations will be irreducible. But unfortunately, there was a gap in the proof, because this condition to say get was with ergodicity. This sub-exponential boundedness was not enough to imply ergodicity.
Where was the if you want to take
No. So that's why we decided to fill the gap. The appears that we should construct more difficult measures. So in our case, measures are more complicated. They depend every time. Collection of measures which we construct, they depend on group which has. For every group, its own collection of measures. So it wasn't that not so natural as this paper, but unfortunately, there is no ergodicity. And we were unable to extend our result to equilibrium case on the that's all.
I mean, well, I have some like maybe irrelevant questions about it. Well, maybe just consider the easier case that we are just considering it like we got a group acting on 0, 1, 2, n. So this is just the right? And so you said that maybe the balloon measure is invariant respect to G.
It depends which Bernoulli method. Only one Bernoulli method is invariant.
It's just like standard, like
It's
one has to be wrong. Yeah. Also not oh.
Then it's never the corresponding Koopman representation will not be reducible because it splits into infinitely many dimensions.
But what about the other stuff, like the total invariant measure spaces of these topological actions? Are there any results of considering this problem? So what are like the other invariant measure considering to this regression group?
But there are no main invariant measures here. In this situation, only one invariant measure.
Only one.
Only one. It doesn't matter. You consider lots of groups, but measure whenever you have minimality property of the groups, which is important. Then there is only one invariant measure for all of them.
And maybe like the entropy of this measure is 0.
It's the action is how to say odometer. So I suppose
Okay. So that's why like the reason why you're like you're maybe not similar and stuff.
exactly.
Okay. Thank you.
Any other questions, comments?
not perfect to the more perfect levels.
Next project.
Okay,
Okay, no more questions. Let's okay.